Good afternoon, everybody. Nice to see all y'all here. Sorry, my Florida came out there for a minute, didn't it? Okay. Today we have a few things to do, so let me make sure the dot cam is firing and I will get us rolling. I appreciate everybody who stuck around last lecture to complete the proof that the derivative of sine is cosine. Today I want to kind of pick up where we left off there. So of course this is MAC2311, Calc 1, section 004. It is a lecture, and today is the 25th of September. And today, we're doing more trig derivatives. And combining trig with the product and quotient rules. All right, so that's the game plan. I want to remind everybody that the exam 1 has, due to the calendar committee's bizarre way of thinking, been forcibly rescheduled to 10/5. So your exam is not next Friday, unfortunately. It will be the Friday following, because in their infinite wisdom, the calendar committee decided Santa Fe has to be closed on October 2nd, even though UF is not closed. The event for which we are closing is UF's homecoming. Don't ask me, I'm not on that committee, I don't know. But if you happen to know any faculty who are on the calendar committee, feel free to barrage them with insults, questions, all of those sort of things. Another mention for today is that study guide one will open today. I'd like to remind you that you need to solve the problem, answer the questions in WebAssign. This counts as homework. But you also need to write out neat solutions, neat, organized, legible solutions as though it's a test. Then scan and submit those solutions in Canvas under the assignment called Study Guide 1. I will be looking at your submissions there as they roll in, and I'll make some comments on them, give you some written feedback, say, if this was a test, I'd take off a half point here, or if this was the test, I'd take off a point here. Please remember this, or please don't do that. All of the little things that you might want to know. So the exam is going to be Monday, October 5th, which is, not next Monday, but the Monday after. Ali asks an important question. Will you need to write out your solutions for the test and then scan and submit them? Yes, you will, but only for the free response problems. So my tests have a mixture of true, false, multiple choice, and free response problems. The free response problems, you will be required to write out nice, neat solutions, and then as soon as the test is done, you'll scan those and submit them to a separate assignment. So there will be 2 assignments in Canvas titled Exam 1. The first will be called Exam 1, take the test here. The second one will be called Exam 1, written work, submit your scans here. So you'll go into the Exam 1, take the test here, answer all the questions. It'll be proctored by HonorLock, all the normal stuff. Then as soon as you're done, you're going to use an app like Cam Scanner on your phone, or if you use an iPhone, the Notes app, to create a PDF of your written work for the free response problems, and you'll submit those. I will be grading the written work. In the test itself, you'll type just your final answer, and then you'll submit the written work to the separate assignment, and I will use the written work to grade the free response problem. So if you do not submit written work, I cannot give you credit for those problems. So it's very, very important. Josh asks, should we do one question per page? Yes, please. One question per page or one question per side. You know, you can flip the page over and put another question on the back, but yeah, one question per page with the problem numbers and your name, please. Again, I'll be posting an announcement with very detailed instructions, exactly what to do for exam 1 when we get a little bit closer. All right. I think that's all the announcement-y stuff. So let me kick off the lecture proper by reminding you what we discovered last time. Just the free response questions. So you don't need to show work for the true, false, or for the multiple choice questions. Those will actually be graded automatically in Canvas, and they're either right or wrong. But the free response questions are graded, you know, there's a lot of partial credit there, right? So the free response questions, I do need your work to grade. Okay. So last time, we proved that the derivative of sine is cosine. And a similar argument shows that the derivative of cosine is negative sine. And from these, we're going to deduce the remainder of the trig derivatives. So that's my first goal today, is to get us through the rest of the derivatives of trig functions and to practice a little bit more using them in the context of product and quotient rules. The other thing I want to do today is introduce some new notation. So the prime notation isn't the only way to describe a derivative. I'm going to introduce it right now. I think we talked a little bit about this when we talked about interpreting derivatives as rates of change, but it's been a while since I've shown you that notation, so here it is. Instead of writing a prime to say I'm going to differentiate this, you can put the symbol d over dx. This is what's called a differential operator. It says take whatever is to the right of me and differentiate it with respect to x. So d dx of sine x is the same as sine of x all primed. That's cos of x. And d dx of cos x is negative sine x. So we talked about this a little bit back in section 2.7, where we talked about dy over dx being like the change in y over the change in x. And one way you can modify that notation a little bit is like this. Okay, so we're just going to practice with both of these notations as we work through examples today. I'll start off gentle. So can we find the derivative of tangent x? Of course, the answer is yes. So if I wanted to prime tangent x, you just have to remember that tangent is sine over cosine. So this is going to be a quotient rule thing. I'll remind you what the quotient rule says. Quotient rule says if you have something like u over v and you want to prime that, that's v times u primed minus u times v prime, that's low d high, minus high d low, over low low, or v squared. So the derivative of tangent, which is the derivative of sine over cosine, will be the bottom times the derivative of the top, and I'll write it out schematically first. That's cos x times the derivative of sine, so I'll write that as cos x times sine primed, minus the top times the derivative of the bottom, that's sine, times the derivative of cosine, all over the bottom squared. That's cos of x all squared like this. So that's just what the quotient rule looks like when applied to the tangent function. Everybody comfy up to here? I'm going to continue over here. Cosine times the derivative of sine is cosine times, well, the derivative of sine is cosine, so it's cosine times cosine, minus sine times the derivative of cosine. Okay, well, that's sine times the derivative of cosine is negative sine. So that's cos x times cos x minus sine x times negative sine x. And this is all over cosine squared. So this is cos squared. Minus minus here makes plus sine squared. All over cos of x. All right, that still is cos of x all squared because that numerator is something nice. What is that numerator?
1.
Yeah, remember the Pythagorean identities for sine and cosine. The first Pythagorean identity says that sine squared plus cos squared, which is what I have upstairs here, is 1. So this is 1 over cosine of x all squared. And what is that?
Secant squared.
Good. 1 over cosine is secant. So 1 over cosine squared is secant squared of x. So the derivative of tangent is secant squared. Sorry, my pen's not playing nice here. So we know how to differentiate sine, we know how to differentiate cosine, and now we know how to differentiate tangent. What's left? Well, secant, cosecant, and cotangent remain. First, any questions on any of these steps here for getting the derivative of the tangent function? Straightforward application of the product rule. You just need to know these, or sorry, the quotient rule. You just need to know these two first. If I wanted to express this in the alternate notation, that alternate notation, by the way, is called Leibniz notation, named after Gottfried Wilhelm Leibniz, the German mathematician who simultaneously discovered calculus with Newton. We would say d dx of tangent x is secant squared of x, right? I.e. that is. Okay. So we still need derivatives of secant, cosecant, and cotangent. Let's find the derivative of secant. How do you think we'll get started here?
One over cosine?
Very good, right? We were able to get the derivative of tangent by rewriting it in terms of sines and cosines. So we should be able to get the derivative of secant the same way. So secant x all primed is the same as 1 over cos x all primed, because secant is 1 over cosine. That's the definition of the secant function. And again, we can apply the quotient rule. That's the bottom times the derivative of the top. So cos x times 1 primed minus the top, which is 1, times the derivative of the bottom. And this all goes over the square of the bottom, like so. What is 1 primed? What is the derivative of the constant function 1?
0.
Good. So that's cos x times 0 minus, what is the derivative of cosine?
Negative sign.
Good. And the 1, I'm not going to write. 1 times anything is just that thing. And this all goes over cos squared x, right? Cos of x all squared is cos squared x. So cos x times 0 is 0. Minus minus makes plus. This is sine x over cos squared x, but nobody would write it that way. I have 2 cosines downstairs and 1 sine upstairs. So I can rewrite this, because fractions multiply straight across, as cos x times sine x over cos x, which is secant times tangent. So in other words, the derivative of secant, hey Hamlet, is secant x tangent x. Oh shit, you better not. All right. So, sorry, I got an update notification. My computer was going to restart. So the derivative of secant is secant tangent, or secant primed is secant tangent. And if you want to write that in Leibniz notation, d dx of secant x is secant x times tangent x. Okay, we still need cosecant and cotangent. Cosecant is 1 over sine. So the derivative of cosecant is the derivative of 1 over sine. This is done the same way as the previous guy. You just swap the cosines for sine. So this is the bottom times the derivative of the top. That's sine x times the derivative of 1 is 0, minus the top times the derivative of the bottom. That's 1 times the derivative of sine is cosine. And this all goes over sine squared. So this is negative cos x over sine squared x, which is very similar to what we got when we did the derivative of secant, right? Compare these. Sines and cosines are swapped, and there's a negative here, whereas there's positive here. So if I want to write this nicely, I'll write it as negative 1 over sine x times cos x over sine x, or negative 1 over sine is cosecant, cos over sine is cotangent. So the derivative of secant is secant tangent. The derivative of cosecant is negative cosecant cotangent. There's a neat pattern there. You swap the function for its cofunction and negate. And this guy in Leibniz notation we would say d dx of cosecant x is negative cosecant x cotangent x. Is this pen dying? Oh, damn it. There we go. Okay, one more remains, and that's the derivative of cotangent. If I want to prime cotangent, that's the same as priming cosine x over sine x, because cotangent is cosine over sine. Low d high, that's sine times the derivative of cosine is sine times negative sine minus high d low, that's cosine times the derivative of sine, which is cosine. This is a cos x, sorry, my bad handwriting. And all of this goes over the square of the bottom. So this time we have negative sine squared x minus cos squared x all over sine squared x. Quick question, can I cancel this into this? Can I cancel the sine squareds?
No.
No.
I mean, technically, wait, you can break it up into 2 fractions.
Right, but as is right now, can I cancel this? The answer is no, because sine squared is not a factor of the top, right? Remember, you have to factor to cancel. It's a mistake I see often, and that's the only reason I'm bringing it up. Cannot cancel these. What can I do here?
Can
I
you
was
pull a
makes one
negative one
point, I
out?
could split up the fraction, but there's another move. What was it?
You can pull a negative 1 out, and you get sine squared plus cosine squared, and then that just turns into negative 1 over sine squared.
Very good. So if I factor a negative 1 from the top, this piece will become sine squared plus cos squared. Everybody see that? Factoring a negative turns that into this. And sine squared plus cos squared, that's 1. So this is 1 over sine squared x. In other words, the derivative of cotangent, right, negative 1 over sine squared x. So the derivative of cotangent is negative cosecant squared x. And that's the derivative of all 6 trig functions. So in summary, I'm going to write this in the Leibniz notation to get us practice. And I'm going to use maybe a different variable. Let's use the variable theta just to see how comfy we are. d theta of sine theta is cos theta. d theta of cos theta is negative sine theta. d theta of tan theta is secant squared theta. d theta of secant theta is secant theta tangent theta. d theta of cosecant theta is negative cosecant theta cotangent theta. And d theta of cotangent theta is negative cosecant squared theta. So this operator notation says differentiate whatever is to my right with respect to this variable. That notation will become especially important when we talk about the chain rule, which we'll be doing next Monday. Any question on these?
I don't have a question about this, but when are we going to learn about derivatives of arcsine and arctangent and all that?
Those are going to have to wait till we have the chain rule.
Okay.
Derivatives of the
Maybe implicit
inverse trig
differentiation
functions.
too?
I'm sorry?
Oh, I'm just saying we do this with implicit differentiation too, right?
Yeah, implicit differentiation is actually a consequence of the chain rule. So you can think of it either way, but yes, you'll differentiate using the chain rule implicitly to cook up the derivatives of the inverse trig functions. I'm not going to hit you with that stuff today because we're about 2 or 3 lectures out from having the tools we need for that. What I am going to ask you to do today is to find some derivatives of combinations of trig functions and algebra functions. So let's play with those. If there are not other questions on this first, including questions about the notation. Do we all remember this ddx, dd theta stuff? Okay. So you may recall one of my early examples when we talked about tangent lines was the function x plus sine x. So let's find the equation of the tangent line to f of x equals x plus sine x at x equals 0 and x equals pi over 2. We're going to find 2 different tangent lines just for fun. As always, we're going to need the derivative. For each tangent line, we're going to need a point and a slope. The slope for both is going to come from the derivative because they're both tangent lines. So first we calculate f primed. F primed here is the derivative of x plus sine x. The derivative of x is 1. And the derivative of sine x is cos x. So f primed is 1 plus cos x. Therefore, the slope of the tangent line at x equals 0 is f primed of 0, which is 1 plus the cosine of 0. What is the cosine of 0?
Negative or 1.
Yeah, positive 1. So this is 1 plus 1, which is 2. So the slope of the tangent line at x equals 0 is 2. What point must my tangent line at x equals 0 go through? The x value there is certainly 0. What's the y value?
Zero.
How do we find it? You're correct, it's 0. How do we find it?
I'll plug it into the original equation.
Very good. So the point of tangency is always a comma f of a. So here that's 0 comma f of 0. And f of 0 is 0 plus the sine of 0. The sine of 0 is 0. So the point here is 0 comma 0. So the tangent line to f of x at x equals 0 follows from the point slope formula. It's y minus 0 equals 2 times x minus 0. Remember that point slope formula. That's hugely important in this class. This is the line passing through x1 comma y1 with slope m. So once you have your point and your slope, you can always write down the line, no matter what it is. Also, the slope of the tangent at x equals pi over 2. That will come from the derivative as well. This is f primed of pi over 2, which is 1 plus the cosine of pi over 2. What is the cosine of pi over 2?
Zero.
Good. So you must know your unit circle to survive this class. If you have friends who've taken Calc 1 here and they told you don't worry about the trig, there's not a whole lot of trig in Calc 1, then they took Calc 1 with someone who doesn't know their shit. Trig is hugely important in Calc 1, so you must know your unit circle. The point is always a comma f of a, so this is pi over 2 comma f of pi over 2. In other words, to find the y value at my point, I need to plug pi over 2 into my original function. So that's pi over 2 plus the sine of pi over 2. What is the sine of pi over 2?
1.
1.
Good. Okay. So this point is pi over 2, comma, pi over 2 plus 1. So now I have my slope and my point. So my line is going to be y minus y1, which is pi over 2 plus 1, equals m, the slope, which is 1, times x minus x1, which is pi over 2. And both of these you could clean up a little bit. This first one, y minus 0 equals 2 times x minus 0, that's just y equals 2x. And this second fellow, if you wanted, you could write as y minus pi over 2 minus 1 equals x minus pi over 2. And then we can add pi over 2 to both sides. That would give us y minus 1 equals x. And then you could add 1 to both sides. So y equals x plus 1. Now, if we were working on a test, I would be okay with you giving me this. I wouldn't tell you that's wrong. This is fine. But if I asked you to graph the tangent line, you would certainly want to rewrite it like this, right? Much easier to graph from here than from here. Any questions about this problem? All right, then let's practice a little bit with the product rule. Can we find the derivative, d dx, of x squared times tangent x? Remember, this is the same as asking for x squared plus tangent x all primed. So what rule am I going to need?
The
Product.
product rule.
Yeah, good, the product rule. I know how to differentiate x squared, and I know how to differentiate tangent x. Question is d dx x squared tangent x equal to 2x secant squared x? The derivative of x squared is 2x, and the derivative of tangent x is secant squared x. So is this true?
No.
No, right? No, because we didn't use the product rule. So derivatives, they play very, very nice with addition and subtraction, but they don't play nice with multiplication or division, and that's why we have the product and quotient rules. Okay, so if I want to calculate d dx of x squared tangent x, I need to write that out as the product rule. So that's the derivative of x squared times tangent x plus x squared times the derivative of tangent x. That's how we would find this. Remember, to differentiate a product, you differentiate one piece at a time, and then you add all of those up. The derivative of x squared is 2x. So this first piece is 2x times tangent x, plus the second piece is x squared times the derivative of tangent x, which is secant squared x. And if we wanted to, we could factor out an x. But of course, you don't have to. Let's try another. What if I wanted to calculate d dy of e to the y times cos y?
Product rule.
Yeah, again, here I need the product rule.
Is that cotangent?
Cosine. So this is d dy of e to the y cos y equals, first I differentiate e to the y and I leave cos y alone. Then I'll leave e to the y alone and differentiate cos y. The derivative of e to the y is e to the y. So that first piece is e to the y cos y. And the second piece is e to the y times the derivative of cos y, which is negative sine y. And so again, I could factor if I wanted to on e to the y, and what would be left is cos y minus sine y, like that. Yeah, very good, Harris. So with these few out of the way, let's take a look at an example or two from your homework. Refresh this, log back in. All right. That's not boring. We just did that. We can do secant tangent next. Why not? Okay, and then we should talk about these special limits too. All right. So while we're having fun with the product rule and trig functions, let's find f primed of x, where f of x is secant times tangent. Again, here I'm going to need the product rule. It might be tempting to conclude something unreasonable because I recognize secant tangent as the derivative of secant. But that doesn't mean the derivative of secant tangent is secant. So what we do is we just jump in, just trust the rules. F primed of x is secant x, tangent x, all primed. And following the product rule, that should be secant x primed times tangent x plus secant x times tangent x primed. The derivative of secant x is secant x tangent x. And when I multiply that by tangent, I'll write it out in this step. I'll get secant times tangent squared. Plus, here I have secant x times the derivative of tangent x. The derivative of tangent x is secant squared x. So this is secant times tangent squared plus secant cubed. Both of which turn out to be very interesting functions from the perspective of Calc 2. But you'll have to wait until the second or third week of Calc 2 for me to show you why these are so damn cool. One more little example here coming from a place that you may have seen in your trigonometry classes. There's a function called cosh, and it's 1/2 e to the x minus e to the negative x. Plus e to the negative x. And another function called sinh, which is 1/2 e to the x minus e to the negative x. These are called hyperbolic trig functions. And because we're learning about the derivatives of regular trig functions this week, I just wanted to introduce these guys. I'm not going to require you to remember these definitions, and I'm not going to test you on hyperbolic trig functions, but I want to show you something cool. If I try to differentiate sinh, that's d dx of 1/2 e to the x minus e to the negative x, recall is 1 over e to the x. The 1/2 will pop out because constant multiples always pop out of derivatives. And what's left is d dx of e to the x minus 1 over e to the x. This first,
I don't think they can do the second one, yeah.
we can, because we have the quotient rule.
We can?
Yeah.
Oh,
So
right,
if you
right,
wanted
right.
to jump in directly, you would need the chain rule, but we can do this with the quotient rule. So d dx of e to the x is e to the x. d dx of 1 over e to the x is the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared, which is negative e to the x over e to the x squared. That's e to the x over e to the x times e to the x. You can cancel one of the e to the x's, and you get negative 1 over e to the x. So the derivative of the hyperbolic sine function is 1/2 e to the x minus 1 over e to the x. Minus makes plus. Yeah, minus negative 1 over e to the x, because this piece differentiates to this, which is 1/2 e to the x plus 1 over e to the x. And remember, 1 over e to the x is e to the negative x. So this is the hyperbolic cosine function. And what's even better is that if you differentiate the hyperbolic cosine function, you don't get negative sinh, you just get sinh. So the hyperbolic cosine functions are even nicer than the regular trig functions. The derivative of the hyperbolic sine is hyperbolic cosine, very similar to how the derivative of sine is cosine. The derivative of hyperbolic cosine is hyperbolic sine, similar to how the derivative of regular cosine is negative sine. So the relationships between the derivatives of these two so-called hyperbolic trig functions, very, very similar to the derivatives of regular trig functions, only nicer. because instead of getting a negative when you differentiate the cosine, you just get regular hyperbolic sine. These guys are hinting at some neat connection between exponential functions and trig functions. I won't say any more than that right now, except that if you're interested in complex numbers, like a plus ib, the square root of -1, like my shirt here, then these guys end up yielding a beautiful connection between the exponential function e to the x and the two trig functions sine and cosine. Okay, I think that is enough fiddling with these particulars. So let's talk about those special limits. You may have noticed that your last few problems in the homework are all limit problems rather than derivative problems. Those are coming from the special limit that we calculated in class on Wednesday. So I remind you, we showed that the limit as h goes to 0 of sine of h over h is 1. This was a special trig limit. That we proved Wednesday. It required a geometric argument where I said, okay, this shape is contained within this shape is contained within this shape. So the area of the smallest guy must be smaller than the area of the middle guy, must be smaller than the area of the big guy. And then we took a limit through that and applied the squeeze theorem. People usually remember this as lim x to 0 sine x over x equals 1. Same thing, right? Just relabeling the variable h as the variable x. I claimed that as a consequence of this, the limit, as we used the symbol h Wednesday, I'll use the symbol x now, of cos x minus 1 over x was 0. Well, let's show that. I'm going to prove to you that this limit is 0 by using this limit. I'll multiply it by the kind of conjugate of the numerator. So I've got my cos x minus 1 over x, and I'm going to multiply by cos x plus 1 over cos x plus 1, like so. Of course, these fractions are grouping symbols. We must think of it like this. And then if you FOIL out the numerator, cos x times cos x is cos squared x. That's my firsts. My outer is cos x, and my inner is negative cos x. Those cancel. So I just get cos squared x minus 1 over x. And you might say cos x squared minus 1, I'm not too sure what that is. But recall the Pythagorean identity. Sine squared x plus cos squared x equals 1. We know this to always be true. So let me subtract 1 from both sides. And then subtract sine squared x from both sides. So cos squared x minus 1 is the negative of sine squared x. So this is negative sine squared x over x. Everybody comfy with that identity work?
Where does the bottom cos x plus 1 go?
Oh shit, it doesn't go anywhere. It's still here, I'm sorry. Sorry, I'm so focused on what's going on upstairs. My bad, thank you, good catch. It's still there. Thank you, thank you. Okay. Everybody comfy up to here? So we FOIL the numerator, and then the denominator, we just leave that as the product, x times prime cos x plus 1. Thank you for the cache there. Any other questions up to here? Are we all comfortable getting to this step?
Yep.
So then I'm going to regroup this as the limit x to 0, negative sine x times sine x over x times 1 over cos x plus 1. Fractions multiply straight across, so if you multiplied these together, you see you will get this, so I can pull this apart into this. And now each of these pieces is relatively easy to manage. The middle term is the hard one, but we've already shown that that middle term goes to 1. He goes to 1 as x goes to 0. So this piece is going to be 1. What do the other pieces do? Well, the sine x, he's continuous at 0, so I can just plug 0 in. The middle piece goes to 1, and the other piece is also continuous at 0. He's cos 0 plus 1. The sine of 0 is 0, so this is negative 0 times 1 times cos of 0 is 1, so this piece is 1/2. 0 times 1 times 1/2 is 0. So that's our other special trig limit resolved. Those two limits are the foundation of everything that you're seeing in the end of your homework. So you have these two special trig limits. Sine x over x as x goes to 0, he goes to 1. And cos x minus 1 over x goes to 0 as x goes to 0. These you need to hold on to. Keep them in a special place and remember them forever. They both require a fair amount of work. So you don't want to have to go through the process of discovering them every time that you use them. So make sure that you tuck those away somewhere special. And when you hear me refer to special trig limits, these are what I'm referring to. It's okay, baby boy. We can solve many problems using these as a basis. Tuck them up here. For example, tangent x over x I can rewrite as sine x over cos x, all divided by x. And I'll continue down here. That's the limit as x goes to 0 of sine x over cos x times the reciprocal of x, which is 1 over x. And now if I rearrange, again, everything here is a product, so I can multiply and kind of pull apart, reassemble. This is sine x over x times 1 over cos x. Sine x over x I know goes to 1. And cosine of 0 is 1. So this is 1 times 1 over 1, which is 1. So just like sine x over x goes to 1, tangent x over x goes to 1 as x goes to 0. There are some other ways you can modify those basic trig limits into interesting stuff. Oh, honey boy, are you okay? It's all right, Bubba, just breathe easy. Sorry, my dog has some like nose tumor right now that's driving him insane. I could play with the limit as x goes to 0 of, well, let's grab one from the homework. Do sine 2x, that's a little boring. Let's start with number 25. Well, I'll modify the numbers a little bit. Let's do sine of 3x over 7x. First, notice that this is the same as sine 3x over x times 1/7. All right, the denominator 7x is 7 times x. I can pop that guy out here. So really, this is my focus. And that doesn't look like my straight up trig limit sine x over x. There's a 3 inside. But if I could introduce a 3 downstairs, that would be nice. Now I've got sine of something over that same thing. But I've multiplied by a 3 on the bottom, so I need to multiply by a 3 on the top as well. Now if we make the substitution, u equals 3x, then as x goes to 0, so does u. So this limit x to 0, I could replace by limit u to 0, sine u over u times 3/7. And this piece goes to 1. So the limit here is 3/7. And all of those limit problems towards the end of your homework use this same sort of trick. Some amount of algebra and substitution so that you can fall back on the sine x over x or cos x minus 1 over x results. I'd like to take a second, give you guys a minute to review both of these and make sure they're clear in your notes and ask any questions. Any questions on either of these kind of special limits? Okay, I think we have time for one more of these wonky guys from your homework. I'll let you choose. 20, we just did 25, right? So 26, 27, or 28. You guys pick. Let me know in the chat. Just open up your chat dialog and type the number you would like to see. 26, 27, or 28. All right, the preference seems to be strongly for number 27. So let's do that. Again, everything is going to hinge on one of those two special trig limits, or maybe both of those two special trig limits. It's the limit as theta goes to 0, cos 5 theta minus 1 over the sine of 6 theta. Neither of these look quite like either of my special limits, but I can start pulling apart and grouping to try and make them look like that. This is cos 5 theta minus 1 over 1 times 1 over the sine of 6 theta. I know that cos x minus 1 over x goes to 0, and I know that sine x over x goes to 1. So what I'd like to do here is introduce the variable theta downstairs here and upstairs here. And I can do that by multiplying by theta over theta. The theta upstairs, I'm going to put here. And the theta downstairs, I'm going to put here. Everything is being multiplied. Oh, sorry, my limit is as theta goes to 0. So I can juggle the symbols around however I want. So this is cos 5 theta minus 1 over theta times theta over sine 6 theta. And now if you think about the previous problem, where I had to introduce the appropriate constants in order to make a substitution. I can multiply by a 5/5 here, and that will give me cos 5 theta minus 1 over 5 theta times 5. So I multiplied and divided by 5, or I multiplied by 5/5 here, and I put the 5 downstairs there and left the 5 upstairs over here, right? So it's like this. And here I'll multiply by 6/6. So that'll give me 6 theta over sine 6 theta times 1/6. Next, I will split up the limit. I'll treat this as lim theta to 0 cos 5 theta minus 1 over 5 theta times 5/1 times lim theta to 0 6 theta over sine 6 theta times 1/6. And in each of these, I'll make a different substitution. So here, I'll let u be 5 theta, and here I'll let v be 6 theta. As theta goes to 0, so does u. So this first piece becomes lim u to 0 cos u minus 1 over u times 5/1. And this piece becomes lim v to 0 v over sine of v times 1/6. What is this limit? Limit u to 0 cos u minus 1 over u. You see it? This guy is the same as this guy. So that piece is 0. So this is 0 times 5/1 times, what about this guy? V over sine v as v goes to 0. That doesn't quite look like this. So if you wanted, you could rewrite this as limit v to 0 sine v over v to the negative first times 1/6. And now sine v over v, just like sine x over x, has to go to 1. So this is 0 times 5 times 1 times 1/6. Or if you like, 1 to the negative first power, which is still 1. Because this piece right here is 1. Right? The sine v over v goes to 1, or if you want, you could say the whole thing goes to 1 to the negative 1. So 0 times 5 times 1 times 1/6 is 0. And that's the game. So these special trig limits require algebra juggling. You want to take whatever your original limit is and manipulate it algebraically until it's some combination of these two special trig limits. Right here at this step, we got our cos u minus 1 over u. I know that as u goes to 0, cos u minus 1 all over u, he goes to 0. That's this special trig limit. And over here, I'm able to get lim v to 0, v over sine v. I know that sine v over v will go to 1 as v goes to 0. So I rewrite this as sine v over v to the negative first power. So now I know the inside goes to 1, so this goes to 1 raised to the negative first power, which is still 1. So altogether, I get 0 times 5 times 1 times 1/6, which is 0. All right, this is where we're going to have to end for today. And good news, this is the cutoff of the material for exam 1. So this is all you are required to know for test 1. It is quite a lot, isn't it? Remember what we started with: graphing, basic algebra, basic limits, very basic limits, limits from the graph, and limits by factoring and canceling, stuff like that. We also have the limit definition of the derivative and the concept of differentiability. The concept and definition of continuity, what it means to be continuous at a point, what it means to be differentiable at a point. The idea that the derivative gives you the slope of the tangent line, and then the idea that the derivative can be thought of as its own function. These are the things that I will be testing you on. So you need to know how to take limits, how to take limits in the easy cases, where the function is continuous and you can just plug in, and how to take limits in the hard cases, where you need to do some amount of algebra and cancel a factor. You need to know what it means for a function to be continuous. You have to be able to tell me the definition of a function being continuous at x equals a, and you need to show me, using that definition, whether a function is continuous or not. Similarly, you need to know what it means for a function to be differentiable at x equals a. And you need to be comfortable showing me, using that definition, whether a function is differentiable or not. You need to be able to calculate derivatives directly using the limit definition. And you need to be comfortable using the power rule, the product rule, the quotient rule, and the rule for derivatives of exponential functions. Finally, you need to be comfortable taking derivatives of trig functions and using and manipulating these special limits. That is the content for exam 1. Monday of next week, I'm going to show you something called the chain rule, which you will not be tested on exam 1. The chain rule will be on exam 2, but because we had to roll our exam date back, I can't just stop teaching. We've got to make use of that time. Wednesday of next week, we will do a thorough review for exam 1. So next Wednesday is going to be all review. The topics I just listed, I will write them down there and we'll solve a problem or two from each category. Friday of next week, we don't have class. Monday of the following week will be your exam. You've got a little bit of extra study time here, more time than we thought you were going to have. Please use it wisely. Do not slack on this. Exam 1, if it goes badly, of course that's not the end of the world. But I want you guys to be building up your confidence. I want everybody to have a good experience on test 1. I want you guys to rock that shit and feel great about it. And that way, as we move through exam 2 and exam 3, you'll have that good feeling, that confidence that it takes to be willing to find time to sink into this class, because it does demand time. If you're not all caught up with the homework, that's the first place to start. After you finish the homework, start on the study guide. I'll be releasing the study guide today. If you finish all of that and you'd like more material to study, by all means, reach out to me. The textbook is a great place to go. And if you don't have a workable copy of the textbook, one that you like, again, you can contact me and I'm happy to help you get this PDF. Okay? That's where we're at. That's where we're going. Any questions before we sign out for the day? see something here in the chat. Yeah, thank you. Oh yeah, of course, you're welcome. Alrighty, then this is where we are going to leave things for the day. Please be mindful of all of the things I just said. Spend time studying, and if you need help, please ask for it. I'll see you either in office hours or on Monday of next week. All right, take care, guys.
Thank you.